Hello, everybody. Thank you so much for coming to the presentation today. So my name is Joshua. I work for Enartis USA as enological manager. And just kind of wanted to start off the presentation with a little bit of information about this new commercial strain of Saccharomyces Uvarum, and sort of line up the discussion with Miguel and the trial that they did at Fresno State. So first, I want to sort of talk about some of the winemaking challenges we're seeing with climate change. We're probably all pretty familiar with what we're seeing, but just so we're all on the same page about this particular topic, we thought we would kind of go through that. Then I'll just give a brief intro to the new strain. Miguel will talk about the Fresno State experiment with some of the data. And then finally, I will talk about some winemaking tips with Saccharomyces Uvarum. So with climate change, we're seeing some regions getting much warmer every year. In the United States, some of the regions that typically were too cold to grow certain grapes might be opening up to new varieties. But some of the regions that were already quite warm are seeing temperatures that can be problematic for the chemistry of the fruit and for the chemistry of the resulting wine. Hotter temperatures in general, we're going to see lower titratable acidity or organic acid in the actual fruit, which tends to lead to higher pHs. With higher pHs, we have issues with microbial stability, oxidative stability, so it's a challenge to have high pH wines. Higher brix, with the ripening that we're seeing with warmer temperatures, we're getting these higher brix numbers. Those higher brix are going to lead to higher alcohols. With those higher alcohols, the wines might be unbalanced in terms of being too hot. So in general, those higher brix can be problematic as well. And then development of overripe flavors and aromas. So we might get some of those raisin notes, might get some of those flavors that just are not really fitting with the style of wines that we're trying to make. So with that in mind, what we're proposing in this presentation is a possible solution for counteracting some of these trends that we're seeing. And that's a proposal of using this technological strain of Saccharomyces Uvarum. We think it's a viable option or an extra tool in the winemaking tool belt to counteract the trends because we think it's economical. It's a passive process, so it's not something that we're actively having to do in the winemaking process. It's something that's happening during the fermentation. It's natural and it's sustainable. So just a little bit of information about the actual isolation of this particular strain. So it was isolated out of Verona in Italy. And when we go to do yeast isolations, typically we're looking for interesting fermentations to do the isolation from. So a winemaker will come to us saying, we have a really interesting fermentation. We think that there might be some interesting yeast in the winery. So come by and we'll try to isolate something. So in this particular instance, this was a yeast isolation from Amarone. If you're not familiar with Amarone, the way that the process is they basically harvest the grapes at a particular maturity level. Those grapes are then dried over the course of a period of time until they are somewhat desiccated. Over the drying period, it could take a month or even more than that before they actually start to do the fermentation. So it's a very interesting sort of winemaking scenario, and it's not something that we typically see in other regions. So with this, we can expect that there might be an interesting fermentation to result from that. And so with the fermentation of the Amarone, we basically visit the winery. We take a sample during the fermentation. We're essentially fishing for yeast at this point. We're taking samples at different points in the fermentation, or even taking the grapes themselves, doing the fermentation and doing isolations at different stages of the fermentation. And so with the results of this particular fermentation, we ended up with the strain of Uvarum that we're going to be describing in the rest of the presentation. A little bit more about Saccharomyces cerevisiae and Uvarum as far as how they're related. So they are both part of the Saccharomyces genus. There's been a lot of really interesting work around categorizing the Saccharomyces genus, and so more recently there's been some really nice work done on sort of differentiating the different strains, or species I should say, of Saccharomyces. And so what we can see here is basically cerevisiae and Uvarum. They're both distinct species. but they're very distant in terms of their genetic makeup and also their fermentation sort of capacity. So the reason why I wanted to show you this is that to show you they're basically very distant from each other within the genus of Saccharomyces, which means that they have different performances. Some of the distinguishing characteristics between these two strains are fermentation temperature. So cerevisiae likes a much warmer fermentation than the Uvarum. The Uvarum we say is cryotolerant or even cryophilic. It actually likes to ferment at a cooler temperature. So the range in cerevisiae is 54 to 97 degrees Fahrenheit. In Uvarum, we're looking as low as 39 degrees up to 86. So very cool temperatures, it actually is okay with that. The other distinguishing factor is phenylethanol production. So this is one of the sort of landmarks for Uvarum, is it actually produces a very high amount of this phenylethanol, which tends to be a sort of floral kind of characteristic. So that's one of the distinguishing factors. Glycerol production is higher in Uvarum compared to cerevisiae. So as part of the pathway of fermentation, it's producing glycerol rather than ethanol, which tends to lower the actual overall ethanol production in the fermentation. The acetic acid numbers after fermentation with Uvarum compared to cerevisiae are quite low. And in fact, some studies have shown that Uvarum can actually consume acetic acid in the fermentation. We can't say that for sure for this particular strain, but this is a potential situation where they're actually consuming the acetic acid. And then high production of succinic acid, which is an organic acid that's produced from Uvarum and Saccharomyces, much higher in Uvarum. And then actually synthesis of malic acid, which cerevisiae you actually have a degradation of malic acid. Uvarum is actually producing malic acid. So this is an interesting characteristic about the yeast as well. So with that sort of introduction to the strain, I would like to bring Miguel Pedrosa up to talk about the work that they did at Fresno State this last year using this strain.
Thank you, Josh.
Good morning. Thank you, Yasha, and thank you to the organization for the opportunity to share these results of an ongoing work with Enartis. And so last summer, I was in conversation with Jose Santos and Yasha, and Brandy Lavoie was still in Enartis at that point. So I talked to them about our need in the Central Valley to improve the flavor profile of our wines. And one of the opportunities for doing this was investigating the effect of non-Saccharomyces, cerevisiae yeast during the fermentation. So with this, one of the interesting things about these new alternative yeasts is that, they offer a new range of, or the metabolites that they produce during fermentation can diversify the flavor profiles. But also, it's important to consider that they have a different performance during fermentation. So all of the characteristics that Yasha was describing before, we know that some of these yeast will be slower fermenters. They will have different kinetics, as shown in the slide. So besides this, one of the things that at least is for primary interest in my lab is studying aromas. And we know that this yeast will have the opportunity to diversify, or at least to add some volatiles that can become more pleasant for tasters. Some of the aromas studied in here or most of the research been done so far is concentrated on esters production during fermentation. And here you have a different profile of two wines, one produced with cerevisiae, another one produced with Uvarum. Probably the main difference in there is that flower characteristic that in some papers has been attributed to phenylethanol. So, and on the ester part, the different utilization of amino acid precursors to produce these esters has also been a reason of differentiating between the aroma profiles of these wines. So with this, the results I'm going to present are actually framed within one of my undergraduate classes where we incorporate undergraduate research experiences for the students. So we have a very simple trial design, just two conditions, one wine with Saccharomyces cerevisiae, one wine with Saccharomyces Uvarum. And the main objective of that experiment was to just increase the complexity of the aromas of these wines. And another important part of the framework is that we're working with Cabernet Sauvignon from our state vineyard. So this is Central Valley Cabernet Sauvignon. And if, as Yasha was saying at the beginning, the warm climate creates a challenge for most viticultural regions, but if you have been in Fresno, we're already pretty hot. So increasing temperatures means that that optimal window where we have most of the aromas is probably shrinking at this point. So we wanted to find an alternative to give a little boost in aroma to these wines. So the primary objective, we're looking for aroma in this experiment. And here you have a picture of the students of the class. Monica and Jose are actually co-authors of this study, and they should be acknowledged. So we hand harvested the grapes from the state vineyard, and then we had a pretty fine protocol. We crushed the grapes the same day of harvest, September 16. Fermentation was done with two punch downs a day, and then the wines were drained and pressed. We inoculated malolactic bacteria, and then we kind of rushed because of the constraints of the class to finishing the wine and filtration by November. The wines were done in duplicate in 10-gallon fermenters, open-top fermenters. So for the cerevisiae, we use Enartis WS yeast, and then we use the new Saccharomyces Uvarum that they kindly also provided. And these are kind of like our basic additions before the start of fermentation. And probably gonna skip this. This is the chemistry of the fruit. And as you can see, this is one of the challenges that we have, at least in our state vineyard. And I see some smiles. And yes, this is the reality for some of our vineyards. We have to deal with a very high TA, very low TA, very high pH. And if you see the brix, well, that was a kind of a standard goal. We have low YANs. And what we know is that all of this will contribute to how the yeast perform. In the original trial, we aimed to adjust actually that TA to 5 grams per liter to have a more standard winemaking juice. So here you have our the average of the 2 tanks of fermentation kinetics. And one of the things that probably I would highlight here is that despite the other or previous research reporting that Uvarum is usually slower in the fermentation, well, you can see a slightly different kinetics, but really the wines went almost dry almost at the same time. So that was interesting to note for the fermentation period. With the finished wines, we sent analysis for the organic acid panel, and all of these results were we got results from ETS. So this is what the first part of the profile showed. And what the first thing that I will highlight is the TA change. So in the cerevisiae wine, you have a TA of 5.8, whereas in the Uvarum, it went 5 grams per liter, almost 5 grams per liter more. And that was something that we were not expecting. It actually took us, the students were actually thrown back, like, where is all this acid coming? So, of course, there was a huge difference in the pH, with a lower pH in the Uvarum. And another important thing was that there was a significant difference in the decrease of volatile acidity. Then, when looking at individual acid or organic acids, I would highlight here in this slide that the concentration, or that big jump in TA that we saw before, it's probably associated with this malic acid concentration. And you cannot see the blue bar of malic acid because it's below the limit of quantification, and which means that our bacteria was successful in consuming pretty much all of the malic acid, whereas in the Uvarum wines, you had 3 grams per liter. And on the white bar in there, you have the concentration of malic acid from the grape juice. It's the same vineyard, a different location of the vineyard. It was not exactly our grapes. We had to dig and find some grapes that actually were provided by Dr. Brillante. But anyway, what I wanted to highlight here is that there was the main driver behind that increase in TA is mainly associated with this malic acid concentration. Then for lactic acid, well, of course, because the cerevisiae was able to go through malolactic fermentation, you have a higher concentration compared to Uvarum. It looks like the Uvarum was also able to, the Uvarum wine was also able to go partially through malolactic fermentation, but it certainly is not, there's certainly a big leftover of malic acid in there. Another significant result there is an increase in succinic acid, also higher for the Uvarum wines. Then when comparing basic chemistry, well, ethanol, we had lower ethanol in the Uvarum wines, a higher concentration of glycerol in Uvarum, and a higher residual sugar concentration as well for Uvarum, although it's still at the low concentration, or many winemakers will consider this dry. So the next part of the analysis was the volatile analysis, and I'm going to present the results as other activity values so that they give you a little bit more of a reference of whether or not these aromas were supposed to be detected, or at least if they are above the threshold. So this, the OAV is defined as the concentration of the volatile compound in the wine divided by the other threshold. And all of these other thresholds are the ones that were collected in the book of Dr. Waterhouse. The analysis was kindly facilitated by Enartis USA and Enartis Italy. And this is GCMS analysis, and all of this, actually all the statistical treatment is just t-test between the two treatments. And here from this slides, probably the biggest differences that I want to highlight first is that production of 2-phenyl ethanol, which is floral rose descriptor, kind of volatile. And what you can see there is that the orange bar is significantly higher than the blue bar, which is cerevisiae. So the floral character, or at least the floral molecules in these wines were significantly higher. And I also wanted to highlight that we're talking here about OAVs of 30, which should be, in theory, very evident for most tasters. There were another differences in also for ethyl esters, ethyl those are fruity, strawberry, apple. So a little bit lower, well, significantly lower in Uvarum. And then difference in 2-phenyl ethyl acetate, which was not significant, so I will not comment on that. The last two compounds that I wanted to highlight here, this one is, on your left, you have beta-damascenone. This is part of the terpene family, and one of the features about beta-damascenone is that it has a very low odor threshold. And if you see the units of OAV, we're talking here about 135, 115 for cerevisiae. So the Uvarum wines were actually higher in concentration for this molecule, which is important because it brings part of that varietal character, or will enhance that varietal character in the wine, probably associated with the beta-glucosidase activity. And then diacetyl, well, the main difference there, it's kind of obvious because cerevisiae wines were able to go through malolactic fermentation, whereas the Uvarum wines had a harder time with it. We took the wines for some sensory tests. We had a panel of 20 tasters, the students and staff. The first test that we did is to alternative forced choice. And here, while working with the students, we had a debate whether the wines were more fruity or more floral. And there was a divided opinion. They decided to go for fruity aroma, and that's how the test was done. And then after the olfactory discrimination part, we also wanted to get a sense of the overall flavor, so we allowed tasters to take the samples and smell them, taste them, and decide which of the two they preferred. And what we found was that for the fruity aroma, we didn't find a conclusive, actually there was a 50-50 divide, so there was no agreement on which one of the wines was more fruity. And for the preference part, most tasters preferred the cerevisiae wine, and the main feedback that we had from there was that the wines were out of balance, especially because the Uvarum wine was extremely tart. The high concentration of malic acid was just not what it was supposed to be, and it was kind of an unexpected. I must say that we were not expecting that high increase in the malic acid concentration. So when we were trying to make sense or arrive to conclusions about these results, well, first we observed that we had this increase in TA and this increase in malic acid, which actually for wines in the Central Valley is very meaningful. Because as you see, we have to deal with those types of TAs and that type of pH. And many of our whites lack that freshness from the beginning. So for us being able to increase that acidity without adding tartaric, that's one of the tools that I can see being very useful for winemakers in hot climate regions, and with climate changing as well, not just in the Central Valley, of course, here and other regions of the world. This is a fantastic tool for, or at least our preliminary results say that, indicate that this is a useful tool to boost that. Then for wine style, lowering the ethanol, having higher glycerol can play on mouthfeel perception, lower alcohol wines. one of the interesting things here that the finding of beta-damascenone and the 2-phenylethanol being able to increase that floral character of the wines is one of the things that we want to continue to investigate. And for this 2022 harvest trials, we're hoping to repeat this experiment, now without adding, without correcting the acidity from the original must, so that we can see how the yeast behaves now with a more extreme environment, because the production of malic acid by the yeast is dependent on the original juice chemistry. So I think we tweaked, or maybe we touched a little bit too much in this trial, but hopefully, we're expecting that this year we'll be able to just use the untouched juice and see how the Uvarum behaves this year, not only in Cabernet Sauvignon, but also hoping to do this in our state Albarino, where we have also that challenge of higher pH than whatever we want. And so another interesting question that we have in front of us is the malolactic inhibition or partial inhibition. We're still trying to figure out that. And also, I think the fact that we saw that big jump in the macedone, concentration of the macedone, that's, to me, it suggests that this yeast has a very potent glycosidase. I must say as well that there were other terpenes in the analysis where we didn't have that jump, but it might be a varietal aspect of our Cabernet Sauvignon at Fresno State, which would be actually fantastic to just figure out if we can boost it with this type of yeast. And with this, I want to thank again the organization, Francesco and Yasha, for support, Enartis, Jose, Enartis Italy and USA for supporting with the analysis. At Fresno State, of course, pretty much all of my students were involved in this trial. Dr. Stefan Sommer and Emily Wilkins facilitated some of the analysis. Dr. Luca Brillante facilitated the grapes together with our farm managers and my department chair and our winemaker, Tom Montgomery. And then I have received as well extraordinary support from ETS for doing this and other trials with my students, so I also wanted to take the opportunity to acknowledge that. So with this, I'm going to call Jasha back.
Yes, we have another part of the presentation by Jasha.
Thank you. So now I just wanted to kind of go through some ideas or tips going forward for how we can potentially use this, this strain of Uvarum. So the commercial name of the strain will be Q-Ro. That's pronounced Ro, not R-H-O. So let's just go ahead and talk about this. So we think that winemakers can control the Saccharomyces Uvarum fermentation with two main levers at this point. One, we think a really cool thing that they could do is actually blending it with cerevisiae. So looking at different ratios of blends with the Uvarum and cerevisiae, and also different kinds of cerevisiae as well. So we could look at a different strain of cerevisiae with the Uvarum for that purpose. The other lever that we can pull is temperature. We know that Uvarum is a cryotolerant yeast, and so we can look at temperature as one of the ways that we can control its fermentation. So looking more at the blending between the yeasts, this was some really awesome work that was done up in BC by Sydney Morgan and others. And basically what they looked at, so this is an adapted version of one of her charts, looking at the proportion of Uvarum and cerevisiae together in fermentation. So on the left side, you have the relative abundance of the different yeasts. So we had a blend of Uvarum and cerevisiae put together in the fermentation. On the left-hand side, that's represented by 10 to 1 Uvarum to cerevisiae as far as the pitch. And then on the right, we have 1 to 1 Uvarum cerevisiae. The larger the white-colored bar is, the more Uvarum you have. The larger the dark bar, the more cerevisiae. And we can see that with the larger pitch of Uvarum, we have a more dominance of the Uvarum in the fermentation. So this is one thing that we can use to control the amount of Uvarum that we're having in the fermentation, is the amount that we use inside of the pitch. And we can see in a 1-to-1 sort of ratio, we actually have more dominance with the cerevisiae. The temperature here is a little bit cooler, 15 degrees Celsius, but I think still the cerevisiae is able to dominate at that particular fermentation temperature. So we're looking at probably, if we're looking at having more of a dominance of Uvarum, is probably a higher proportion, maybe 2/3 or even 3/4 of your total pitch will be Uvarum, with 1/4 or even 1/3 of the cerevisiae. And you pitch them both at the same time, basically. Sort of looking at these, the idea of blending these two together. If we wanted to sort of get complexity without getting too much in one particular direction, so if we wanted to get some of the influence of the Uvarum, then what we can do with these blends is we can actually taper some of the effects here. So we see that by using a blend of Uvarum and cerevisiae, we can actually modulate the amount of alcohol that we're getting, so we can get lower alcohol levels than just the cerevisiae alone, but maybe not as low as just the Uvarum. So we can play around with this a little bit. For residual sugar, this is another reason why we might want to use a cerevisiae inside of the fermentation complementary with the Uvarum. While this strain of Uvarum is actually quite alcohol tolerant as far as Uvarum goes, we still could potentially have some conditions where we have maybe higher alcohol fermentations, or more difficult fermentations where we would want to have that cerevisiae present to make sure that we can finish at the very end. So this is another reason why we might want to do blends with this particular strain. Although you could use it on its own as well. So looking again at sort of using blends to modulate the amount of effect that we have, we can see that with malic acid production, we get a similar effect where the blend has lower production of malic acid than the pure strain of Uvarum. On that same note, I just kind of wanted to touch on this a little bit. If we're talking about sort of counteracting some of the winemaking effects of climate change, I thought I would also touch on some of the CO2 footprint that comes with organic acid additions. Most of the organic acid that is exogenously added by winemakers actually comes from Europe. So that organic acid has to be transported in bulk over the United States. And so that obviously has a carbon footprint as far as the transit. If we look at sort of naturally increasing the malic acid with yeast, we actually have a significantly lower amount of total weight required to achieve the similar amount of organic acid. So if we were to compare an organic acid addition to using the Uvarum, we would see roughly 25% less weight of actual product transported from Europe. So that's a decrease in the carbon footprint. So it's probably a drop in the proverbial press pan, so to speak, but it's, we need to do everything that we can as far as lowering our CO2 emissions, so it's something worth looking at. Kind of going back to looking at blends and their effects, so 2-phenylethanol was one of the aromatic compounds we were talking about. Using a blend, we can sort of modulate that effect as well. So just kind of looking at blending this yeast with cerevisiae, I think is quite interesting. Looking at the other lever I mentioned earlier, temperature. When we look at the preference of growth for Uvarum and cerevisiae, I think that this could be actually a very good way that we control the dominance between a blend. So what this might look like is having a particular temperature profile where we pitch the Uvarum and cerevisiae together at a lower temperature. And then when we are happy with the amount of Uvarum fermentation we have, we bump up the temperature and allow the cerevisiae to dominate. So we can play with temperature in order to trigger the dominance of one of these two strains. So as an example of that, let's say we were doing a cold soak and we pitched the Uvarum at the same time as the cerevisiae. In the very beginning, we might have some of that Uvarum fermentation happening where we're getting production of malic acid, production of 2-phenylethanol, production of succinic acid, and then we might basically get to a point where the cerevisiae takes over once the alcohol gets to a certain percentage or once the temperature bumps up to the point where it can dominate. Something else that we could do is we could have a cooler fermentation that's consistent. So we have a temperature-controlled fermentation where we're maintaining a 55-degree fermentation. The Uvarum is dominating. And then let's say we get to a malic acid point that we're happy with, then we could bump up the temperature and let the cerevisiae take over. So these are just some ideas of how we can use temperature to modulate the blends of the Uvarum and cerevisiae as well. Some other future work that I would like to see using the strain, lowering VA in compromised fruit. So we've seen from studies that Uvarum is able to consume acetic acid. And so I'm interested in looking at the yeast for this particular purpose. Cold soak fermentations I think could be really interesting, seeing if we can get, let's say, a fairly gentle fermentation happening at low temperatures, almost like a cold soak. Different blends of Uvarum and cerevisiae I think will be really cool to see. So using white strains of cerevisiae, red strains of cerevisiae, and combination with the Uvarum, I think that could be really kind of fun. Beaujolais-style reds I think could be really interesting with Uvarum for its capacity to lower VA levels, also working at lower temperatures. So these are just some ideas going forward for how I think this strain could be used. Again, the commercial name of the strain will be Enartis from Q Row, and we will have it in production for this year if you're interested in trying it out. And we do actually have a commercial blend that's already Saccharomyces cerevisiae and Uvarum, which is the U42. And we've been using this really successfully for the last 3 years in various different regions with different kinds of wines as well. So I just want to say thank you to Miguel and Fresno State for for the hard work that they did on their trial and sharing their information to the students and staff as well. Thank you to the Enoforum for allowing us to present this information today, and thank you for your attention.